Welcome back. We're going to continue talking about measurements, and we had ended our last discussion talking about derived units. And remember, none of these units exist. These are all when you get things and put them together. Those base units are put together. So let me just give you a quick little example here. So area and volume are what are called derived units. If we were to look at this, area means length times width. So length can be maybe 5 meters, width 3 meters. When you put this together, you get a unit of meters squared, which is not a base SI unit. It is instead what is referred to as a derived unit. So the area for that square would be 15 meters squared. If we're to do a volume, volume is also a derived unit. And so if we do volume of this box here, it'd be length times width times height. And so if I have a length given width and height, I multiply those together, I get a volume. This time the unit for that is meter cubed. So that's what I mean when I say the term derived unit. Alright, there are metric prefixes I need you to memorize, to know, and I've listed those all here. All of these, mega, kilo, deci, centi, milli, micro, and nano, I'm going to ask that you memorize. Now, you probably already know kilo means 1,000, right? If back in the 80s, there's a lot of people carrying cocaine around, and if they carried a kilogram of cocaine, that was a lot of cocaine. They were going to prison for like 1,000 years. If that helps you remember, kilo means 1,000. Deci, that means 1/10. Don't confuse deci with deca. Deca, D-E-C-A, is 10. Deci is like the decimal of that. So they're like 10 dimes in a dollar. That's the deci portion, right? It means 1/10. And centi means 1/100th. There are 100 years in a century. And there's 100 cents in a dollar. So centi means 1/100th. Milli, well, think about a millipede with its 1,000 legs, or maybe a millennium, 1,000 years. The prefix milli means 1/1000th. Now you can add these to anything. You can have a millimeter, that's 1,000th of a meter, or you could have a milligram, 1,000th of a gram. So the prefixes can be applied to any of the base units of the metric system. Micro, he was that guy from Dirty Jobs on TV. He did all those jobs, and pretty cool guy. Anyway, Micro is like one of those 1 in a million kind of guys, right? He's got a sense of humor, he works hard, he can sing, he has a personality. And so micro, and it looks like a cursive U when you write it, it means 1/1,000,000th, or 10 to the negative 6th power. Nowadays, scientists are making things incredibly small, down to the nano scale. Nano, it means a billionth of something. So a nanometer is a billionth of a meter. Very, very tiny. Now, if you play the lottery, maybe you win big and you win the mega millions. Well, mega means million, or 10 to the 6th. So I want you to know and memorize those prefixes. When we think of measurement, oftentimes we think of in a laboratory something like a graduated cylinder. It is a piece of glass in a cylindrical shape that has, well, I say graduated, earned its degrees, or has little lines on the side of it. And it would be used to measure precisely volumes of a liquid. But there are other instruments that could be used to measure liquids in a lab. I've shown them here. The first one is called a graduated cylinder. The second one you might call a syringe. That would be fine. We won't use syringes. We're not going to have needles around. This next one's one that you're probably not as familiar with, and it's called a burette. If we get to class, we'll actually use those in the solutions chapter. And this next one is called a pipette, or a transfer pipette. And the last one is a volumetric flask. At this point, I don't need you to know the names of those pieces of glassware or equipment. If we use them in class, then that'll be different. I'll remind you what they're called again, and I may ask you to know those names. If you're wondering how much is a liter of water compared to a quart, well, basically they're the same amount. Are in 1 liter 1,000 milliliters, but 1 quart 946 milliliters. So there's roughly 4 liters, like 3.84 liters in a gallon, if you're trying to keep it straight in your head. When you're reading the volume in a graduated cylinder, you want to make sure that you are reading the meniscus eye level, right? If we were together, I would do a bunch of deep knee bends and put the graduated cylinder on a very low table, and I would drop my knees down to get my head low enough, and I would keep going up and down, and you realize very quickly that's not how you make a measurement. Instead, you hold the graduated cylinder up to your eye level to make the measurement. And when we look at it, we don't measure from the top, and maybe we measure from the bottom. How about where the slope is 0? See here how it has a negative slope? Here it's a positive slope. So right at the bottom for this one would be where we would measure, where the slope is 0. Okay. Now if you measure from too low, you're going to artificially get the wrong value. And so that'll be too low if your line of sight is too high. And likewise, if your reading is too high, you would get a reading that's too high if your line of sight's too low. So instead, hold your eye right at the eye level of where that slope is 0 on there. So it's where I've shown it, right in the middle there. That would be the correct place to sight that and make your final reading. In terms of comparison, I guess, a kilogram, if you're wondering, is equal to about 2.20 pounds. So if you were trying to figure out, well, how big is a kilogram, right? So if somebody says they weigh 200 kilograms, they're actually pretty big, aren't they? If they weigh 200 kilograms? Yeah. Right? All right. This kind of gives you a comparison in terms of orders of magnitude or size. So if you're looking at a water molecule, it's down here about 10 to the negative 24th grams. A protein, maybe 10 to the negative 19th grams. A grain of salt, 10 to the negative 7th grams. A liter of water, maybe you'd say how much for a liter of water? I hope you'd say 1,000 grams, because that's what we said earlier. The average human is going to be up here, an average Indian elephant here, an ocean liner 10 to the 12th. Here is the Earth's atmosphere and all the weight of that, right? So it's a huge range here that can be covered. And of course we have prefixes that we could use for those. We've mentioned mega, kilo, milli, micro, and nano. Those are ones you need to know. You don't need to know pico, femto, atomo, or giga, right? And there are others. I put them on here. If you want to impress your friends and memorize these, I will never ask you any of those that aren't in black. Okay, so don't worry about all the other funny sounding ones there. All right, we've already hit scientific notation. I could review, but I don't want to waste the time on this particular video, so I'm going to skip through this section. I'll skip through that. We've done conversions before. This is sort of showing us here's an equality. 1 inch is equal to 2.54 centimeters, so we could come up with 2 conversion factors that relate to that. Again, this is maybe not the spot I want to be dealing with conversion factors in this lesson right now, so I'm going to skip through this slide. Let's talk about the difference between accuracy and precision, because I'm not sure we sometimes use those terms interchangeably and they mean something very different. So let's pretend we have a dartboard and we're going to throw darts at that. So I throw my first dart, I'm aiming toward the red center, and I throw it, and I aim a little bit high. Okay, so was I accurate? Well, not really. I mean, I didn't hit the bullseye, so I wasn't that accurate. Was I precise? Well, it turns out we can't answer that question with one throw. Precision has to do with the repeatability of a measurement, meaning over and over again you get the same value. That's what precision means. I throw another dart. Boom, I hit up here. I'm still not accurate, but I am precise, aren't I? Because both of those came very close. And I'll throw a third dart. And there it is. Again, I was aiming for the red, and I was high and to the right every single time. So I would say those 3 throws were not accurate, but they were precise. Now, it could be that I just need to get a new prescription for glasses because maybe they don't work very well at this distance. If I were shooting rabbits in my backyard, not that I would do that, but if every time I aim high and to the right, I'm going to aim a little bit lower and to the left, and then I'll start to get rid of those rascally rabbits. All right, let's try another one. All right, so we're going to say that's poor accuracy but good precision. So we'll try again. This time I'll have you throw a dart. So go ahead and toss one. Aim for the red. Oh, I thought you had it there at the beginning. Throw another one. Okay, I see you're compensating. You went left the first time, or right, and then you went left. Let's try for the middle. Throw one more. Go ahead. Oh, you're back over here. Now, if I were to say, were you accurate? Not really. Were you precise? Not really. Was that useful data? Well, probably. If you averaged your 3 throws, they would be very, very close to the center. So on average, if we collect enough data, you will be accurate. But in this case, you're not very precise. So we could say poor accuracy, poor precision. In the last example, I'll have, well, I don't really care. I'll have an AP student throw these darts. They tend to be a little bit more precise. Go ahead. Go ahead, throw one. Wow, that was thrown behind his back and it hit right there. All right, you go ahead and throw one. Whew. I mean, you threw it from my left and it came from my right. That was pretty impressive. All right, let's throw one more. Mr. Chapman, hey, go ahead, throw one for me. A dart at the target. And that's why you're the principal, right? Because you hit those things, right? Good job. All right, look. Those 3 people threw 3 darts. They all hit the bullseye. So were they accurate? Yes, each of them were accurate. Were they precise? Collectively, they were precise because they were closely grouped. So good accuracy and good precision. That's what we're after. Now, if you see poor accuracy but good precision, this is usually due to an instrument needing to be calibrated. So let's talk about random errors that reduce precision versus systematic errors that reduce accuracy. Okay? Random errors are the person that's throwing it, the person that's making the measurement. They're going to make random errors, right? The systematic errors reduce accuracy can generally be corrected because these have to do with the instrument being calibrated properly. I don't know, you've never actually seen me in person, but I'm not that big of a person. I'm about 6 foot tall, relatively slender. And if I stepped on a scale and it said I weighed 308 pounds, there would probably be a problem with that scale because you can adjust the little adjuster on the back of the scale to make somebody look like they weigh more or less. So that would be a systematic error if every time I step on the scale it says I weigh that much. Now, precision versus accuracy. Accuracy means you're correct, you're close to where you should be. And precision is measured after multiple measurements to see if they're reproducible. So precision has to do with reproducibility. Accuracy has to do with were you correct. So again, those systematic errors, the instrument maybe wasn't zeroed properly. Somebody had misadjusted it. Or something you were using wasn't mixed properly. So everything's off by a little bit. Okay? Those are systematic errors. Random errors are maybe there's an air conditioner that keeps kicking on the room and changing something. Or the person running the test doesn't really know what they're doing because they weren't properly trained. Okay? So depending on if you see accuracy issues or precision issues, you know where the problem lies. Again, systematic things tend to be an error in one direction. Either all your measurements are high or they're all low, and they can be corrected through proper calibration. or running what's called a control to set your instrument up. Random errors, they can go up or down and every place in between. Sometimes they'll actually be correct. And if you see random errors, that's not the instrument, that's the person running the instrument. It can't be corrected. The only way you can overcome or account for random errors is running lots and lots of tests and then averaging the final results. That's why in science we don't make just one measurement, but we make multiple measurements and average those to get rid of those random errors. Another way to look at this instead of a dart would be, actually, let's collect data. So the time offset 0 is our target. So if every one of these dots represents a data point, you can see that our data tended to be a little bit high and it was spread out quite a bit. So I would say you weren't very accurate and you certainly weren't very precise. It was all over the map. In this next example, if this is our target, we were a little high, we were a little low, and we were spread out, so we maybe were not particularly precise, but if you average that, we're probably accurate. If you look at the average of all these throws, you were right on there, but not very precise. In this example, we were closely grouped our data, so it is indeed precise, but it's not very accurate. It's too high. So it's not accurate, but it is precise. And this last example, this is maybe what we'd like to see in our data. It is both precise and accurate. It might be you're a chemical engineer and your job is to monitor the filling of boxes of cereal, and you don't want the boxes to be too full or not enough cereal in them because you'll get complaints. And so you probably are looking for something like this, where all the boxes of cereal have pretty much the same amount in them. All right? We won't worry about that last column there, about that at all. All right. So prefixes, you should know kilo means 1,000, deci means a tenth, centi means a hundredth, milli means 1,000th. What does micro mean? 1,000,000th, good. And nano? 1,000,000,000th, good. What about mega? 1,000,000, good. And so those are the prefixes I need you to know. I also need you to know that 1 milliliter is equal to a centimeter cubed, and a liter is a decimeter cubed. We'll use those throughout the year, so it's useful if you have those in your knowledge bank. All right, that's just a slide. If you're looking, here's the unit km, kilometer. So I'm using the kilo with the base meter. So a kilometer is 1,000 meters, or 10 to the third meters. And I've done several of these here for you can kind of see what they mean, what they represent. And I won't say any more about it. You can look if you need to. We want to talk a little bit about how you make a measurement with a ruler or a thermometer, because students inevitably don't know how to properly record a measurement using this instrument. In our class, we will always use a centimeter for measuring. Remember, we don't use that 4-letter word inch on the English system. But if you are comparing, 1 inch is 2.54 centimeters. So let's say we want to measure the length of this nail, and we're measuring in centimeters. Well, let's zoom in a little bit here. We want to use significant figures because in a measurement there is a certain amount of precision. And the precision has nothing to do with how good your eyesight is or how good you are at estimating things. Precision is determined by the instrument that you are using to measure. So in a measurement, you write down what you know with certainty and you estimate one uncertain digit. So we get to add one I want to say decimal or digit, I'm kind of stuttering there, one decimal beyond, or one digit beyond what the instrument shows. So let me show you what I'm talking about here. If we look at the tip of this thing, if we look very carefully, we know that here is 6.12, here's 6.3, and it's beyond that, but it's under 6.4. So 6.3 is not a correct measurement, 6.4 is not a correct measurement, but 6.35 centimeters is a correct measurement. I could have said 6.31 centimeters and I would have been correct. The 6.3 I know with certainty, and then I estimate the next digit. Now 0.1 is not a very good estimate, but I couldn't mark it wrong if that's what you put. I could have also called it 6.39 centimeters. Again, the 6.3 is known with certainty, and if I estimate that as 9/10 past, it's a terrible estimate, but I have to give you credit. If you wrote 6.350 centimeters, you are incorrect. You are estimating 2 digits of uncertainty, and that's not allowed. Imagine if I called that 6.3500002618 centimeters. You know I'm making up those numbers. So we're only allowed to make up one number, the last digit. Now let's try this one. If we are right here, well, I got a better one. Let's do this one here. All right. So I've got that red box on the screen, and here's my instrument. Now the instrument is a ruler that only goes by the whole number of centimeters. So I know the centimeters by ones with certainty, which means my estimate goes to the 10th of a centimeter. So if I look at this carefully, it's between 4 and 5, so it's 4 point, now you put any number you want. I might call that 4.5 centimeters, and I would be correct. If you call that 4.1 centimeters, sadly, I'd have to give you full credit. If you called it 4.9 centimeters, again, sadly, I would have to give you credit. If you call that 4.50 centimeters, you are incorrect, because we only get to estimate one digit. Remember, you don't determine the precision of a measurement, the instrument that you're using does. If I use a more precise instrument, notice now that the instrument, the ruler, goes by tenths of centimeters, which means my final measurement will need to be given to the 100th of a centimeter. So now if I look very carefully, like this little guy here, I see we're just a hair past 4.5, but not at 4.6. So I might say 4.54 centimeters. 4.5 with any number after it would have got you correct on that example. Again, let me remind you, in the first example, the ruler only goes to the ones place, so our measurement needs to be recorded to the tenths place. On the second example, the instrument measures to the tenths place, so our measurement is recorded to the hundredths place. In the last example, this goes to the ones, which means our final measurement needs to be to the tenths place. Because that looks like it's precisely on the line 3, if I wrote 3 centimeters, it's not correct. I would need to write 3.0 centimeters to earn full credit for that measurement. I'm not going to worry about implied uncertainty. I'll click through this, but you are by no means needing to know this. If you say something's 5 centimeters, you mean it's 5 centimeters plus and minus then a half on either side of that. So when you say 5, it could be anywhere from here to here if that's what you write. If you write 5.0 centimeters, this is the implied range of what you're measuring, and you see that's much more precise. And if you write 5.00 centimeters, that's what you mean. So how you write a measurement means something to somebody that understands it. All right, let's practice measuring a liquid in a graduated cylinder. So I've got a graduated cylinder here. I'm going to pour some liquid in there. There it goes. And now the question is, where do I read that from? Right? You know, do I read it from up here? Maybe. Do I read it, it could be anywhere you want, I guess. Do I read it from down here? Maybe. Well, the answer is you read where the slope is 0. Water adheres or sticks to the side a little bit, and because of that, the true volume would be where the slope is 0. So this is a negative slope, this is a positive slope, right at the bottom is a slope of 0. So you hold right up to your eyes there. Now you look. This instrument, if it's in milliliters in the graduated cylinder, goes by ones, because here's 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So if it goes by ones, our final measurement needs to go to the tenths of a milliliter. So if you said 15 milliliters, unfortunately, you're wrong because you didn't write it to the correct amount of precision. And this is what I started with, saying students think they know how to make a measurement, but they really don't. So instead, we would write that as 15.0 milliliters, or if we wanted to put that in scientific notation, we could write 1.50 times 10 to the first milliliters. Again, in scientific notation, all three numbers in front are significant. Okay? All right. I'm going to skip this whole section on Verniers. I spent a huge amount of time animating these things for you. If you want to go through that and look at it later, you can. I'm not going to ask you any of that on my test at all. Let's practice reading a thermometer. I've got some very simple ones here. Let's see what we come up with. So notice that if this is 0, 1, 2, 3, 4, 5, these go by 1, so my instrument goes by 1, so my measurement needs to be to the 10th of a degree Celsius. So this looks like it's right on the line here at 4, so I might call that 4.0 degrees Celsius. Let's try this one here. Now this one's a little bit trickier, isn't it? 1, 2, 3, 4, 5, 6, 7, 8, and a little bit past. So we go by ones, so we need to have it go to the 10th. So how about 8 point, and then you throw out a number. I like that number. 8.2 degrees Celsius, 8.3 degrees Celsius would be okay. Would 8.25 degrees Celsius be all right? No, because then you're adding too much precision that the instrument does not have. This one's a little bit trickier. If we look at this, the instrument, we go, here's 10, 20, 30, 40, 50. So it goes by tens. So the tenths place, so we have to go to the ones place for our estimate. So if this is 50, this must be about 62, 64, somewhere in that range would be okay. Okay? 60 something would be okay. This last example here, we're going by very small amounts because every 2 lines is actually 1. So we have to go by maybe a half. So that would be 3.5. Here's 1, 2, 3.5 degrees Celsius. I have some more here for you to practice. Again, I'll let you pause. You can then think about what you would get, and then when you're done, go ahead and hit start again, and I'll give you the answers here. That first one, I would get 30.0 degrees Celsius. It goes by ones. I need to go to the tenths. The second one, 3.00 degrees. It goes by the tenths, so I need to record to the hundredths of a place. The next one is 19.0. After that, 48 degrees Celsius. And finally, 60 with a decimal, or 60.0 degrees Celsius. All right, I hope that makes a little bit more sense on how we record a measurement. It's not maybe as simple as you thought it was going to be. So measurements we certainly will use. Now this summarizes some stuff for us. In the metric system, we have all those things we can measure. We'll talk about derived units later. We'll have to deal with prefixes and how they relate to conversion factors, and then how we solve problems with those. And then of course we need to report our final answer with the correct amount of uncertainty using the right number of significant figures. So it's not simply a matter of getting an answer, it's showing me the work, showing me the setup, getting the right amount of digits in your final answer with the correct unit. All right, let me see if there's anything else I want to talk about here. I'm going to skip all this stuff. I will probably hit a few more topics with you, but we're getting real close to the end here. Thanks again for sticking around with me, and I hope this stuff is making sense. Again, we'll finish this and pick this up a little bit later. Okay, bye-bye.